Hi, and welcome to the third part of our discussion of the life cycle of stars. We're continuing to kind of skim our way through some of the chapters, chapter 20, 21, 22, on into 23, I believe, of OpenStax Astronomy. When last we left off, our stars that had been burning in the main sequence had run out of hydrogen to fuse in their cores, had done a slight collapse, and were beginning to fuse hydrogen in their outer layers, causing those layers to begin to expand, which then caused them to cool and begin to turn red. So we were in the early stages of the formation of red giants. What we're going to look at today is actually a couple branching paths, and that depends largely on how big a star is before it enters into this phase of its life. What we refer to as a regular sized star, that's something that's really more along the lines of the size of our own sun, will spend the bulk of its life in the main sequence as previously described. After it begins its expansion, when it begins to run out of hydrogen to fuse into helium, it will go through a fairly fast contraction and crunch, which will result in a big surge in temperature and pressure at its core, which will cause the helium to begin to fuse and form carbon. It's what's referred to as a helium flash. This is of a special note to us because as carbon-based living things, we owe to a large degree the existence of the carbon atoms that make us up to events like this that happen in the core of these late-stage stars. Now, whenever this helium flash happens, there's a return to a larger size. There's also a big release of energy and matter that kind of swings out in an ever-growing ring of material. And we're going to talk more about those here in just a few minutes. We'll see another repeat in events. The helium in the core will burn for a short period of time until it begins to run short, and the star will contract some, causing helium that's outside the core to begin to ignite and then fuse into carbon, which will cause another partial expansion of the star. In some larger regular-sized stars, that carbon that's in the core will undergo another fusion event where it will join up with more heliums and begin to make atoms of oxygen. Most of these regular-sized stars won't ever grow beyond this phase. If they exhaust all of that helium fuel and begin contracting again, then they never hit the right kind of temperature or pressure to cause those oxygen and carbon atoms to fuse into even larger ones. And so then they begin to enter their final death phases, which we'll talk about the next video. More massive stars, which are decidedly larger than the sun, remember they live their life on a very short time scale. Because they have so much material, they get to the main sequence much more quickly, they burn through their hydrogen much more quickly, and then begin to fuse helium. Now with them, they don't really have a big crash event that starts their helium fusion because there's plenty of matter and plenty of pressure and gravity and that enables it to begin fusing that even while hydrogen is still being fused further out. What happens with these more massive stars, which swell and become red supergiants, is that they do have enough matter to continue contracting and fusing increasingly larger and larger elements all the way up to helium. And what we're going to talk about toward the end of this presentation is once they're fusing iron, then they are very, very close to a very catastrophic death. Look at an HR diagram for a regular-sized star after they leave the main sequence and begin to swell into a red giant. Once they run through that fuel, they'll contract, and then boom, you've got a helium flash which catapults them back up to giant status. You can see what's kind of going on in a cross-section of the star here, where at the core of the star we've got carbon and oxygen which has been fused, followed by a core of helium outside that. Some of that core is being fused. Outside that, you've still got hydrogen fusion going on. As mentioned a second ago, what happens when these stars contract and then re-expand is they do give off up to about a quarter of their total mass in these very large outflares of gas and dust and energy. We refer to these as planetary nebulas. Now, it's not that it has anything really to do with planets. It's just that the first time astronomers saw these, they were round and reminded them of planets. And in astronomy, names have a terrible way of getting stuck, which is why it's astronomy and not astrology. But anyway, the name stuck. And depending on your point of view, when one of these planetary nebulas occurs, if you happen to be looking at it perpendicular to the expansion of that cloud, then you see what looks much more like a ring. Whereas if you happen to be looking at it from any other angle, from directly outside of it to any angle in between there, then it takes on more of an hourglass shape. And planetary nebulae are really some of the more beautiful phenomena in the observable universe. This slide right here, which I've linked to down there if you want to get a closer look at it, shows a number of different planetary nebulae, and they're absolutely beautiful. And you can see at the core of each of these, there's still a star that is living out its last few million years, but it's having a really good time doing so. It's going out on top, going out in style. Your supermassive stars, which become your red supergiants, like Betelgeuse, which we've discussed before, they are going to give off even more stellar material over longer, more prolonged periods of time. Again, they are only existing a fraction of the time that you're going to see a smaller main sequence star exist and go through these stages. You can see in the cross section right here, we've got lots going on, and you've got different elements being fused at different depths out from the core. The reason why iron is kind of the end point is up until iron, all of the different elements, carbon, oxygen, magnesium, neon, silicon, sulfur, etc., whenever they're fused and make new daughter atoms and new daughter elements, more energy is being given off than it is required to take it in. Once you get to iron, there's an energy deficit. It takes more energy to fuse iron into something bigger than you would get out of it. And so as a result, if you think of these big stars kind of like celebrities that are kind of on a train wreck downhill lifestyle, going faster and faster and faster, and you just know any day now you're going to see some kind of terrible, terrible death that they've gone through. These stars have spent any fortune that they had. They have lived very, very fast, and they are heading for a very catastrophic, cataclysmic death, which we will talk about next time. And when we talk next time about how a star dies, we'll also answer the question, well, if elements up to iron are made in these red supergiant stars, what happens to cause all of the elements bigger than iron? And we'll answer that the next time. Thank you very much for joining us.